Welcome to this explainer. Today, we're taking a journey from the super simple idea of ideal point particles all the way to mastering the complex everyday movements of real-world objects. Let's jump right in.
Here's our roadmap for today. First, we're going beyond the simple particle. Then, we'll talk about finding the center. Third, translation versus rotation. Fourth, the magic of rolling. And finally, energy and motion.
All right, Section 1. Beyond the simple particle. Let's start by challenging how we usually think about objects in basic physics. We typically just pretend objects are tiny, infinitely small points. And hey, it makes the math super easy. But picture a heavy bowling ball for a second. What is actually physically happening as it rolls down the lane? It's definitely not just a microscopic dot gliding through space, right?
In our daily lives, that idealized model of a particle is just totally inadequate. Real bodies actually have a finite size, and in physics, we call them extended bodies. Because they have actual physical dimensions, they can deform, they can warp, bend, and most importantly for us today, they can rotate. So to really grasp the physics of the real world, we absolutely have to account for the whole body, not just a single point.
Which brings us to Section 2, finding the center. To understand how these extended bodies actually move, we first have to find their anchor point. So let's dive into this concept of the center of mass. This acts as the absolutely crucial anchor for literally any physical body we study. By definition, the center of mass is the mass-weighted mean position of a system of particles. But honestly, you can just think of it as the mathematical balancing point. It's the spot where all the mass of the object behaves as if it were concentrated into a single, perfectly balanced point.
So how do we actually find this magical point? Well, locating the center of mass really depends on how the object's mass is distributed. It's calculated using coordinates and mass weights. If you've got two objects of equal mass, the center is exactly at the midpoint between them. Easy enough. If you have an equilateral triangle made of three equal masses, the center sits right there at the centroid. And what's incredibly elegant is that for uniformly distributed, symmetrical objects, like a solid ring or a perfectly balanced bicycle wheel, this center perfectly matches up with this geometric center. You look at a bicycle wheel and you know right away its center of mass is sitting exactly at the axle.
Moving on to Section 3, translation versus rotation.
Now that we have our center locked down, we need to isolate the two very different ways an object can actually move. Placing these concepts side by side really helps clarify the boundaries between an object sliding and an object spinning in place. In pure translation, the center of mass physically moves through space, and every single point on the body moves the exact same distance in a given direction. But in pure rotation, the center of mass is completely stationary. It doesn't travel anywhere at all. Instead, every other point spins in the circle around that fixed axis.
A sliding block moving down an inclined plane is a perfect illustration of pure translation. Assuming there's no sideways slipping or tumbling, every single point on that rectangular block, from the top corner all the way to the bottom edge, is moving together with the exact same velocity at any given instant. They are totally synchronized.
Conversely, think about an oscillating table fan with rotating blades, or even a spinning ceiling fan. The axis is completely fixed. That central pivot point is stationary, right? But the blades trace these perfect circles around it. The distance from the center dictates just how large a circle each point on the blade traces. And that, my friends, is the absolute definition of pure rotation.
Okay, Section 4, the magic of rolling.
Now it's time to slam these two isolated variables together and see what happens. And here is the big aha moment. A rolling object is simply experiencing both straight-line movement of its center and spinning around its own axis at the exact same time. It's a combined motion. Rolling literally equals translation plus rotation.
So let's visualize this combined motion with a solid cylinder rolling down the same inclined plane. Think about the velocity at different points on this rolling cylinder. Unlike the sliding block we looked at earlier, the particles here are actually traveling at entirely different velocities at any given instant. It's kind of wild, but the top edge of the cylinder is actually moving through space much, much faster than the center.
And that brings us to a really fascinating concept, pure rolling motion. We define this as a combined motion where the point of contact with the surface has exactly zero velocity relative to the surface. Wait, what does that mean? It means the very bottom point of a rolling object, like a cricket ball, momentarily comes to a complete rest the precise instant it touches the ground. Because the backward rotational motion perfectly cancels out the forward translational motion at that exact specific point, the ball doesn't slip or skid. It just grips and rolls.
Let's see how this builds into the mathematical condition for pure rolling without slipping. First off, this entirely relies on having enough static friction to keep the object from sliding. Second, both the translational and rotational motions must be completely perfectly synchronized. And this synchronization gives us the golden formula, v equals r times omega. Simply put, the linear velocity of the center of mass perfectly matches the radius of the object multiplied by its angular velocity.
Section 5. Energy in motion.
Finally, let's look at how we measure the kinetic energy of an object that is doing both, moving forward and spinning at the same time. The absolute best part here is that we don't need to invent any complicated new math. Because rolling is just a combination of those two motions we discussed, the total energy of a rolling rigid body is literally just the simple sum of its translational and rotational kinetic energies. You take the standard kinetic energy for translation, 1/2 mass times velocity squared, and you just add the rotational kinetic energy. That's the whole shebang. Just add the two parts together.
Before we wrap up, I want you to keep this rapid-fire summary of common pitfalls in mind when you're tackling rigid body dynamics. First, always apply V equals omega r for the no-slipping condition. Second, make absolutely sure you use the correct moment of inertia, that's represented by I, for the specific shape you're analyzing. A solid cylinder has a completely different value than a hollow sphere. Next, keep your units consistent. Carefully distinguish between tangential variables, like standard linear velocity, and angular variables, like rotational speed. Always draw clear free body diagrams to map out your forces and torques. And above all else, never confuse pure translation, pure rotation, and combined motion. They each have very distinct physical behaviors.
So the next time you see a bicycle wheel rolling down the street, are you just going to see a simple circle moving forward? Or are you going to see the hidden combination of translation and rotation working together in perfect harmony? Will you picture that exact bottom point of the tire coming to a complete, momentary stop before lifting back into the air? I really hope this explainer has changed the way you look at the moving world around you and leaves you completely curious to spot the physics hidden in your everyday life. Catch you next time.